Okay, we're up and running now. So right away I'm going to share my screen. So you guys should be seeing my screen now. Welcome everybody, and I want to, I know I told you about the assignment yesterday, and so some of you may have gone in and done a bit, maybe today, let me show you some further examples, and then that may answer some of the questions, but then we'll have more of the student questions toward the end. So hopefully, I think that might work out a little bit better today, because some of your questions might be answered with some of the exams I would like to do, but I would like to see if there are any questions on the concepts I presented last time. So any questions from last time? I mean, it's not like I'm just going to make start after it. We're going to do a little bit of review too. Maybe I'll just dive in and do that. So, so when it comes to our, let's see, I got to get back here and find out where I am. Yeah, get my mouse in the right spot. So yesterday we talked a little bit about the difference between, you know, the familiar difference quotient up here on the top. Let me get my pen up and active here. So, you know, we had the difference quotient up there on the top, and that's why that's there. And that's nothing. That's exactly the same as that's a slope. In fact, that's where we got this. This is just all we did to obtain that was to do the y-coordinate of the second point minus the y-coordinate of the first point divided by the x-coordinate of the second point minus the x-coordinate. So all that is a slope. So that makes sense that that's there. And then we added this concept that we also call the average rate of change, because what you're doing is picking 2 points and find the rate of change is nothing more than finding the slope. So we did that yesterday. And then you all know that if we add this circled thing, the limit, if we just take the limit as h approaches 0 of that difference quotient, now we have a derivative. And now instead of an average rate of change, we've got what we call the instantaneous rate of change. Okay, so that's review. And then, you know, we did an example. So to find average rate of change on the interval that you see over here on the right from, by the way, excuse me, I'm sorry about the cold. I'll try to keep that kind of interruption to a minimum. But as we were to find the average rate of change over the interval from 0 to 1, all we did is found the 2 points when x is 0, y is 180, so there's our first point right here. And then when x is 1, or t, excuse me, when t is 1, that gave us negative 16 times 1, negative 16 plus 180 is 164. That gave us the second point, and then we just did the slope. Okay, we came up with an average rate of change of negative 16. Remember, this was a falling object, and so the negative indicates gravity's effect pulling it downward. Okay, so we did that. Yeah, and then I just gave you kind of a look ahead to apply this to word problems, especially in physics. The function is usually a distance function. When you take its derivative, you've got what? The instantaneous rate of change of the distance. We call that velocity. Welcome, Sword social media editor. And Camilla is obviously having problems. She got dropped out again, but hopefully she'll be able to come back or see the video. And then if you take the rate of the instantaneous rate of change of the velocity, that's what we call that acceleration. And then we can even sometimes go the instantaneous rate of change of the acceleration is sometimes called the jerk. Okay, so let's all review. And remember, we also took a look at this problem, this example from the book from page 109, where we had a guy diving off a diving board, and the equation was given on the top there. And the question was, when will he hit the water? So when will his height be 0? So you notice in this line right here, I set it equal to 0. And then that was algebra. How do you solve a quadratic set equal to 0? You try to factor it, and you notice I divided both sides by -16, and then you come down to here. And now we can easily factor it. T plus 1, t minus 2, set each factor equal to 0. We came up with 2 answers. Remember, we even made sense of the -1 second answer. That is, had the parabola gone back down, you know, whoops, grab that. Had the parabola gone down, let's see, get my pen again. No, it doesn't want. There we go. Had the parabola gone down on the other side, then it would have been -1 second before. And the one we wanted is it takes 2, we found 2 seconds. That's the one. So it took him 2 seconds. Now the question was after that, all right, how fast is he going when he hits the water? Well, remember what I just showed you in the previous screen? When you have the distance, which was h of t, I mean that's the height, distance, how do you find the velocity? Oh yeah, it's the first derivative. Okay, so what's the first derivative of the function? So you just do the power rule. 2 times -16 is -32. Reduce the power on t by 1, t to the first. The derivative of 16t is 16, and the constant goes away. So here's the general derivative for this particular problem. Now, what's the exact velocity at 2 seconds? And that's what we found out down here. What is h prime at 2? And a little bit of substitution. He was going when he hit the water, he was going 48 feet per second downward. Okay. Excuse me. Then yesterday I also showed you some things about business. I know you know these probably, but we had profit equals revenue minus cost. We learned a new word, marginal. Whenever you see marginal thrown in, that basically means rate of change or derivative. So if C of x is the cost, then C prime of x is the marginal cost. If R of x represents the revenue formula, then the first derivative of the revenue is the marginal revenue. And then we threw in, you know, if small p, maybe I should just write here small. If small p stands for demand, this is an equation that will come up. Revenue equals the number of units or items that are produced times the demand. That'll equal the revenue. Okay, and then we started doing examples. I think what I'm going to pass. Let me just ask this. Last time I did number 5 and number 8. Did anybody want to ask any questions about number 5 or number 8? I see we still don't have Camilla, so she had some problems. So anybody, any questions on 5 or 8 from last time? If not, what I'm going to do is start some new examples then today. 5 was this one. Yeah, I know. If you look in the book, they gave you a function and they said, sketch the graph and find the average rate of change and compare that to the instantaneous rate of change at the endpoints. So here you can see, well, here, I'm going to just go on to the new. Okay, so let's talk about number 10 in the book. We never were here last time. If you look at number 10, this is on page 116. We see that we have the function g of x equals x cubed minus 1. And we're supposed to analyze this on the interval on the closed interval from -1 to 1. And the directions say, use a graphing utility to graph the function and find its average rate of change on the interval. Okay, so I'm going to use Desmos to do this. So here's Desmos. And first of all, here's a graph of x cubed minus 1. If it was just x cubed, it would go through the origin, but because it's minus 1, it's shoved down 1. And then I highlighted, what was the interval from -1 to 1. So I found these 2 points, this one right here, -1, 2, and this one right here. Those are what? The ends of the interval that they asked us to examine. Okay, then I found, if you connect the two, let me get those points out of there now. I can't remember how to take, anyway, I can't remember how to get rid of points, but if you connect the 2 points, the slope of that line, that's our average rate of change. So why is it average? Because it just goes from the endpoints of the 2. Again, I'm trying to find how to turn those off. There we go. So anyway, goes from one endpoint to the other. What's the slope of that? That's the average rate of change. Okay. Well, I mean, if you just look, you can see that from here to here, there's a rise of, it goes from -2 up to 0. So a rise of 2 and a run of, from -1 to 1, a run of 2. 2 over 2 is 1. So what's the average rate of change on number 10? 1. Okay, now let's come back for a second to our pad here. So let's just write average rate of change is 1. Okay, we did that from the graph like the book wanted us to. Now, they want us to find the exact rate of change at -1 and 1. So, first, let's do a little calculus here. In order to find the exact rate of change, we need to take the derivative of the g function. Well, derivative of x cubed? Well, power rule says 3x squared, right? Because 3 times x reduce the power on x by 1. This is a constant. -1 is a constant, so the derivative of that is gone. All right, so now what's g prime at the point -1? -1 squared is 1. 3 times 1 is 3. All right, and what's the exact rate of change at +1? And it turns out to be the same, right? Because 1 squared is 1. 1 times, so you can see that these two are not at all the same as the average rate of change. Now, let's quickly go back and look at the graph. And I've got a little, I did a little work here. Here's the 1 point on the interval, and if we throw the tangent line to the curve right at that point, I think you can see it's got a slope of 3. That is, let's see. So if you go over 1, you will go up 3. Oh yeah, 3 over 1, slope of 3, just like we found. And on this other interval endpoint, the tangent line is the same slope. So you can see they're both 3. And why? And you know what's going on here. The tangent line would change to what? A slope of 0 right here in the middle, and then goes back. So it's high, then it goes down to nothing right here, and then it comes, and then the slope gets bigger again. So I don't know. Anyway, that's what number 10 is about. They wanted you to graphically see what the average rate of change is. We could have done it with algebra 2. And then they wanted you to compare that to the exact rate of change at those 2 intervals. So anyway, that's our first new example. Then I want to do number 12. Let's talk about that one. It's pretty graphical, and sorry, this is a little bit distorted, but you know, take a picture of a page in the book, and because of the margins and the binding, things get curved. But anyway, number 12, medicine. The graph shows the estimated number of milligrams of pain medication, M, in the bloodstream T hours after a 1,000 milligram dose of the drug has been given. So, you know, when you first take the medicine, nothing. And it's in there for an hour, and it's up to this amount. Here, I guess I'll do that in red. And then after 2 hours, it's getting higher. 3 hours, we're up to here. And then, of course, the medication wears off. After 5 hours, we're down to there. And after 6 hours, basically the medication is worn off. So now, part A says, estimate the 1 hour interval over which the average rate of change is the greatest. Now, the average rate of change would simply be, you know, like, let's see, how can I put this? So, if we just connect, let me get rid of those red dots, because I was using that to show you something else. Okay, now, the first interval, the first hour interval goes from here to here. Right? It's just, you know, when you hit the 1 hour strike. And if you connect that with a line, let me attempt to do this. You know, the slope of that line is what we're talking about. That's the average rate of change over the first interval. Okay, then the second interval would look more like this. And do you see how that slope is a little bit bigger? And then the next interval goes from here to here, and that would look something like this. See how that one's a little bit less tilted up? And of course over here, if we go from here to here, whoop, that wasn't. If you go from here to here, now what's going to happen when you connect those two? It's getting shallower and shallower. So the question is, can you tell me the 1 hour period? And by the way, it's going to get negative over here, right? You can see it's going to start going downhill. So estimate the 1 hour interval over which the average rate of change is the greatest. Would you say it's the first hour, the second hour, or the third hour? It looks to me like the second hour, because this one is a little steeper here. Let me get rid of those drawings now, those lines, because now they're kind of clouding the issue. So between which 2 hours is the slope the greatest? And I think you'd agree it's from 1 to 2. So this is just a graphical visual problem. That's what's going on there. On part B, it says, over what interval is the average rate of change approximately equal to the rate of change at t equals 4? Okay. So at t equals 4, we're right here. Here, let me get rid of these reds again. getting a call, which I cannot accept right now. Sorry about that. Hang on just a second. Hello, Thomas. Okay, I'm in the middle of a broadcast, teaching to my class. What can I do for you? Okay. 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 Could could I call you? Could I call you back to reschedule? Because I'm right in the middle. I will do that. I'll call you back. Thank you. Thank you, though, and I hope your daughter is better. Yep. Bye. Yeah. Sorry. Roofing contractor calling me. Had an appointment. He's got to cancel. Okay. So anyway, we were at part B. So at t equals 4, we're right here. What is the slope of the tangent line right there? Well, would you agree it's something like this? That appears to be approximately the slope of the tangent line right at that red point. Now the question is, can you tell me which hour interval has the closest to that slope? Well, that's not a real easy answer, because if you took this hour from here to here, you would get this slope. Well, that's certainly not the same. And if you took the hour from 4 to 5, you would get this slope. Which one is better? I don't. You could argue they're both different. I would say either the interval from 3 to 4 or the interval from 4 to 5. It's kind of right in between. So kind of an odd question. So what they're trying to get you to do here is they're trying to get you to see the difference between this instantaneous slope that we get when we do a derivative and this average rate of change, which actually connects 2 points. So anyway, I could see B going either way, either the interval from hour 3 to hour 4, or the interval from hour 4 to hour 5. Okay, another one. Let's take number 14 from the book, top of the right column on page 117. So, chemistry, wind chill. At 0 degrees Celsius, the heat loss, H, in kilocalories per square meter per hour from a person's body. So we're talking about when it's a certain temperature outside, how fast is your body going to cool down? That's basically what we're talking about here. H is the heat loss. You know, how much are you going to lose per hour? And you can see that they actually gave us the equation. Here it is, where V stands for the wind speed and H stands for the heat loss. Okay? Now, this might get you a little bit. It says find dH dV. In effect, what they're saying is find H prime. I mean, this is really here. This is really H of V. They're saying find H prime of V. So in other words, this is saying find the rate of change of the heat with respect to the wind velocity. Okay, so we know how to do that. It's just a good old derivative. So let's do that work. I need a little space here. So now let's see. I gotta have the function showing. So here we go. So let's write that as H of V instead of H, and let's multiply this thing out. Still not very friendly for taking a derivative, is it? So let's rewrite this. And what we're going to do, now remember, we don't have a way really at the time to take the derivative of a square root unless we go to what? Rewriting a root in power notation. So 330 v to the what? 1/2 minus v plus 10.45. Now we can take the derivative. What's h prime of v? Well, take the exponent, 1/2, multiply it by the coefficient. Half of 330 would be 115. And now reduce the power by 1. And then what's the derivative of minus v? I mean, that's like v to the 1. So it's, what happens is you get -1 times v to the 0, and v to the 0 is, so it's just -1. And this guy is a constant, so he goes away. So there's our derivative. Let's just rewrite it. In algebra form, we would get 115, and then the v, the square root of v would go on the bottom. Why is it a square root? Because of the 1/2. Why is it on the bottom? Because of the negative. So there's our general derivative. Okay. Now you can see, so we've done part A. Part B says, find the rates of change when of h, when v is 2. So in other words, what's h prime at 2? So we simply plug in a 2 for v. And then let's call up a calculator to do some of this. So we've got what? 115 divided by, I'll say parentheses, 2 square root equals. You know what? I forgot to multiply 33 right here, didn't I? I just realized I made an error up here. My apologies. This should be right here. I'll highlight it in red. This should be minus 33v. Sorry about that. Okay, so this is minus 33. Yeah, the bottom line is, so this is minus 33v. And then when you take the derivative, you get minus 33 here. There's our derivative.
Okay, okay, you got it. Never mind.
What? Joey, did I miss your question?
Oh no, I didn't know I was live. My bad.
Oh, it's okay. Anyway, what's the getting back to my calculator now? I've got this, and I have to subtract 33 to get my last part. So this one turns out to be 48 approximately. Okay, so that means when it's 2 degrees Celsius, the human body will be losing about 48, what do they call those? Kilocalories per hour. I'm not, so anyway, it's not degrees, but it's a form of heat measurement. And then the other part is what is it at 4? I'm sorry, at 5. So what's h prime at 5? So now I should change to blue here. 115 over the square root of 5 minus 33. And again, let's calculate that out. So now we have 115 divided by 5 square root, and then subtract 33. And this time we get what? 18.4. So obviously it's warmer here, and by the way, these are Celsius. They're bigger. So when it's 2 degrees, you're losing 48 kilocalories per hour. When it's 5 degrees Celsius out, the body loses 18.4 kilocalories. So sorry about that error. I took that derivative wrong in the beginning. I forgot to multiply that 33 out, and you know what? This number should have been bigger too. It doesn't really matter, right? That should have been about 330 approximately. But again, it doesn't really matter because when you take the derivative, this is going to be gone here. So I did a lousy job of my distributive property. I should have multiplied 33 by each of the terms. So this was really just a derivative problem, a little bit of algebra first, then find the derivative, and then find. So first, this one here says find the general derivative, and then in part B, find the specific derivatives at 2 and at 5, which we did down here. Okay, next example, number 18. This is pretty short and sweet. Remember what marginal means? Marginal something means the derivative of that. So in number 18, they give you the formula for cost. The cost for X items is 104,000 plus 7,200X. By the way, when it comes to costs, this cost, the part where it's just a constant, that means that's pretty much, that represents what? Capital cost. Like I gotta buy a machine, a stamping machine, or a paint gun, or whatever. That's just overhead, stuff you have to buy or you can't make your product. And then this is the cost of making, each item costs them 7,200 to actually, man hours and electricity and that kind of thing. All right, so what's the marginal cost if that's the cost? Just take the derivative. And isn't this a really easy derivative? Sure. I mean, constant, that's the derivative of a constant is gone. What's a derivative of something times x to the first? It's just 1 times 7,200, 7,200. Reduce the power by 1, x to the 0, which is 1. Nice and easy problem. So knowing what marginal means comes up there. We've got 2 more examples to look at. Number 20. Number 20, same part. It says find the marginal cost for producing X units. So on number 20, here's what they gave us for the cost. They said 100 times the quantity 9 plus 3 times the square root of x. Well, we need to multiply out that distributive property there. That's what I did in the second line. 100 times 9 is 900. 100 times 3 times the square root of x is 300 times the square root of x. Notice, though, I didn't write square root of x. I went to the exponential notation. Why? Because I knew in the next step I need to take a derivative. Okay, so now take the derivative. What's the derivative of a constant? Nothing. What's the derivative of this? We can use the power rule here. Bring the power down. What's 1/2 times 300? 150. Now take the power and reduce it by 1. So now I have 150 x to the negative 1/2. This is written algebraically like this. Right? Negative means downstairs, and the 1/2 means root, second root. Okay, so there's your general marginal cost. And if they ask you, what's the marginal cost when you're making 100? When you're making 4? They didn't. this is really the end of the problem. I was obviously showing students, if they asked you for the marginal cost when you produce 100 items, and when you produce 4 items, then you could go ahead and find the specific. One more example I'd like to look at. I'm trying to get a variety of these. Let's take a look at number 41. Okay, here's where that R equals PX is going to come into play. Number 41, business problem, and it says the demand function for a product is given by small p equals 50 over the square root of x. So that's this thing right here. That's the demand. All right. And they give us this, notice they limit the domain to from 1 to 8,000. Why do they do that? Well, I mean, if you don't make at least one, why are you even there? I mean, it's stupid to go into business to make 0 products. So it's got to be above 1 or equal to. And the reason it's less than or equal to 8,000 is maybe that's the capacity of their current equipment. Can't make any more than 8,000. So anyway, that's why there's a limiting factor there. Okay. They also give us a cost equation. They say it's 0.5x plus 500. That's this one. Okay. Again, that one's limited. Again, you can't have it. Yeah. Anyway, we don't have to talk too much about that. But did you notice? They never did give us the revenue equation. So where did I get it from in the square box? I got it from here. Remember? Just earlier today we talked about this equation. To find the revenue, you have to take the demand times x. So I had to take this guy right here in the square and multiply it by x, which I did in the box here. See how I took 50 over the square root of x times x. And then the only reason I multiplied the top and the bottom by the square root of x was to rationalize the denominator. Nice thing happens on the bottom, you just get x, and on the top you just get x times the square root of x. So the x's cancel, and we're down to, there is your revenue. Okay, now that I know the revenue, and I know the cost, so here's the revenue, right here, and here's the cost. Now can I find the profit? Yeah, now I can take revenue minus cost equals profit, and that's what you see right here. Profit equals revenue, 50 times the square root of x, which I wrote this way, minus the cost. You guys see why that's a minus sign right there? Because when I subtract the quantity 5x plus 500, I have to subtract both, right? The old distributive property. Okay. And what did they ask for? The marginal profit. So now that we have the profit, how do we get the marginal profit? We take the derivative. What's the derivative of 50x to the 1/2? Power rule. 1/2 times 50, 25. Take variable and reduce exponent by 1. X to the negative 1/2. Derivative of negative 0.5x, negative 0.5, the constant, gone. So, here is our derivative, not in algebraic form. And then in the book they say, I didn't do all of them, but for part A they said, what's the derivative when you're making 900 units? And so now we find P prime at 900. What's the square root of 900? Why am I doing that? Because x to the negative 1/2 means square root. The square root of 900 is 30. And what's 25 over 30? 5/6. So I did a little bit of simplifying there. Minus 0.5 or 1/2. Okay, what's 5/6 minus 1/2? Get a common denominator. 5/6 minus 3/6 is 2/6, and 2/6 reduced. to lowest terms is 1/3. So what's the marginal profit when you're producing 900 items? A third of a buck, or 33 cents. And then they go on and they say, all right, what's the marginal profit when you're making 1,600? And I didn't, but again, you just go back, substitute in 1,600 for X, and okay. So there's a pretty good variety of problems. I hope good enough for you guys. I already had shown you the assignment last time. Here it is again. And now, I may or may not have answered some questions, some anticipated questions. So let's open it up to questions here. So please, anybody, and send me a text message if you want. Any questions that I can try to clarify on? So now we really have a full lesson 2.3. We didn't quite have enough time yesterday. So I did some rehashing that should help you. Just going to check my text messages here. Don't seem to have any. All right, I'm not hearing anything. You can certainly write to me, call me, text me. I will see you hopefully tomorrow. Sorry about the growly voice, the sneezing and the coughing. Hopefully that'll be going away. I'm starting to feel a little bit better. Thank you.